Welcome to our discussion on flowcharts and algorithms. In the next 10 minutes or so, we will discuss two related concepts, flowcharts and algorithms. Let us start with algorithm first. Algorithm is essentially a logical sequence of well-defined steps to carry out a task. So why do we qualify steps as well-defined? So the adjective well-defined is there to imply that the steps are meaningful and executable. Meaningful so that they make sense, executable so that we can carry out the steps. So any logical sequence with the well-defined steps will define an algorithm. What is that logical sequence? They cannot be random collection of well-defined steps. There should be a reason as to why we write these steps in a particular order. So there is a logical sequence that is essential to construct an algorithm. Let us look at an example. For instance, you want to instruct your friend to start a car. So, in fact, you can find them in any manual that comes with a car. The first step, for instance, could be insert the key in the keyhole below the steering wheel. Next step would be to turn the key clockwise. Subsequently, you hold the key in the turned position till the engine starts and then release the key. If it is a well-maintained car, these steps should enable you to start the car. Since every step in this algorithm is well defined and there is a logical order in this, for instance, you cannot expect the car to start even before you turn the key clockwise. Therefore, there is a logical sequence to these steps. So this defines a good algorithm. So this is a very nice example of a good algorithm. Let us look at another algorithm. Let us say you want to tell your friend how to reach the chocolate factory which is next to our campus. So there are 5 steps given here. 1. You walk 150 meters towards south. This is a well-defined step because we understand what is walking. 150 meters and also the particular direction that is mentioned here. Step 2 says wait. Now is it a well-defined step? Wait for how long? Somebody may choose to wait for an hour. Somebody may choose to wait for days. Somebody may choose to wait for eternity. So it is not a well-defined step. Step 3 suffers from the same problem. Think about what, how long, what is expected after thinking. So this is once again a step that is not well defined. Of course, you realize steps 4 and 5 are well defined. So as a whole, this algorithm is not a good algorithm because there are 2 steps in this which are not well defined. Presence of even one step will render an algorithm to be not useful. Of course, you can modify step 2, say wait for a minute to see if traffic is less and then move to step 3. So that will make step 2 meaningful and executable. Maybe you can take it as an exercise so that you can modify step 3 to make it well defined. So we have seen an example of a good algorithm and another example of an algorithm which is not good. The previous 2 examples will appear to be something that you cannot do with a computer. In the context of computer science, algorithms often involve mathematical operations. Essentially, there are 2 major classes of mathematical operations, arithmetic operations and logical operations. Arithmetic operations involve manipulation of numbers and the result is once again a numerical value. So we are familiar with very many arithmetical operations, addition, subtraction, multiplication, division, exponentiation and many more. Exponentiation probably may require some explanation. So exponentiation is the process of raising a given number to the power of another number. For instance, when I say 2 square is 4, I am raising 2 to the power 2. 2 power 3, which we commonly refer as 2 cube, is 8. But it's not the case that it should be an integer. For instance, you can talk about square root of 25, which is 5, in which case we have raised 25 to the power 1 half. Cube root of 8, for instance, is 2, in which case we have raised 8 to the power 1/3. So these are all arithmetic operations. Another class of operations which are very useful when we deal with problems is logical operations. So logical operations do not yield numbers, but the result is usually either true or false. For instance, we can have a statement like 5 greater than 2, then logical operation would mean the result is true. You can say 8 is less than or equal to 8, the answer is true. 8 is not less than 8, but this statement is about either less than or equal to. Therefore, it is true statement because one part of the two possibilities, less than or equal to, is true. Therefore, it is true. 8 less than 8, of course, is false. So we have seen two major classes of mathematical operation, and in this course, we will be essentially encountering these two operations in designing good algorithms. Now let us take a very simple algorithm to add 4 numbers, let us say 1, 4, 3 and 10. So how would you instruct somebody to add these 4 numbers? Here is the sequence. As step 1, you take the first number. As step 2, you add it to the second number to get a sum, say S1. In the next step, you add this S1 to the third number to get another sum which you call as S2. So S2 now involves sum of first 3 numbers. Now add S2 to the fourth number and whatever you get is the result. So these are the steps involved in summing up 4 numbers. There's nothing sacred about 4 numbers here. You could have taken 10 numbers or more. It is just an example to tell you that arithmetical operations are useful in calculations. To give an example in a very familiar context, let us look at making an equilateral triangle using turtle. I'm sure all of you would have done this in your classes, but here is the algorithm to do that. First step is to move the turtle cursor by 10 mm. The next step, you rotate the cursor by 60 degrees towards left. Then move the cursor forward by 10 mm. Rotate the cursor by 60 degrees towards left. And then finally close the curve by moving the cursor forward by 10 mm. Realize that each step in this is well defined. So moving the turtle cursor by a given length or rotating the cursor through an angle are well defined operations, and therefore this algorithm is indeed a good algorithm. Now let us come to flowcharts, which is essentially a diagrammatic representation of algorithm. It's a pictorial representation of algorithm. So there are elements which are combined to make flowcharts. Typically you have a circle, you have a parallelogram, you have a rectangle and a rhombus. So each of these elements are designated for a particular purpose. For instance, input-output operations are usually represented using parallelogram. Start and stop operations are represented using a circle. The mathematical calculations or steps are represented using a rectangle. The rhombus is usually used for branching, transfer, or condition. We'll understand what this branching implies shortly. So now let us look at a very simple problem, that of calculating an average speed of some object. So any flowchart representation of algorithm will always start with the start. So you have a circle in which you write start. Now I need 2 inputs to calculate the average speed. Input 1 will be distance, input 2 will be the time taken. Because these are input operations, I need to use parallelograms. So in the first parallelogram, I write input distance. In the second parallelogram, I write input time taken. Now, calculation of average speed is a mathematical operation. That is dividing distance by time. Because it's a mathematical operation, I enclose it in a rectangle. So that is the fourth object in this flowchart. Once I calculate this, I will be able to output this number for other users. So I use a parallelogram to represent the process of writing the output, which is write average speed. Once this job is completed, the algorithm is over, and therefore I write stop once again within a circle. So this is how a typical flowchart will look like. You would notice that this flowchart has not used rhombus as yet. There is no requirement for branching in this particular problem. So let us look at another problem which would involve branching. Here we want to draw 4 successive lines oriented in different directions using turtle. So as usual, we will start with a circle start. So I am having a counter called movement, which tells me movement number 1, movement number 2, and so on and so forth. So I have to keep counting how many movements I have made. It's a mathematical operation. Therefore, I put it in a rectangular box. So I initialize it as movement is equal to 1. And to draw the line, I need 2 parameters, input length and input angle. Therefore, I have 2 parallelograms which will allow me to collect values regarding length and angle. After that, I have to instruct the cursor to move forward through the length L by an angle T. So that's a mathematical operation. Therefore, I enclose it in a rectangle. Having drawn the first line, now I have to draw the second line. That is my second movement. Therefore, I make movement increase by 1, which I call as an increment. So whatever movement appears on the right hand side is the previous value. To this I add 1 and I get a new value for movement. If you notice, we started with a movement equal to 1 and here there is no change of movement. Therefore, in this box, movement becomes 2. It's a mathematical operation, therefore it is enclosed in a rectangle. Now I have to perform this operation 4 times because I need to draw 4 successive lines oriented in 4 different angles. Therefore, I have a rhombus here to make a decision. I ask, is the movement less than 5? Because I don't want to cross 4. So if the movement is less than 5, of course, I go back and ask for the next length and the next angle, move the cursor by that length and angle and increase the movement. Let us say this I might have done 4 times. I start with 1. I would have drawn the first line and first angle. Then movement becomes 2. I go here, I draw the second line through this angle specified for the second line. Movement becomes 3. Since it is less than 5, I go back here. Therefore, I draw the third line. It becomes 4. Since it is less than 5, I go back and I draw the fourth line. It becomes 5. Movement becomes 5. But the question here is movement less than 5. Once movement becomes 5, it is not less than 5. Therefore, this condition is invalid. That movement is less than 5. Therefore, the answer is no, false. And that takes you to stop the algorithm. So this is one simple example where we need to use rhombus because there is a decision to be taken depending on, in this case, the value of numerical value of movement. So this brings us to the end of the discussion. Now I have a few questions that you can think about. Make a flowchart for these 4 problems that I have indicated. And if you have an introduction to Python already, then you can also make a program using the flowchart to guide you. Thank you very much.